I'm just going to review the previous lecture. You have come across three different mechanisms for aromatic electrophilic substitution reaction. You have come across orinium-ion mechanism. Most of the compounds show this mechanism, but some limited one you have come across can follow our SE1 mechanism. So there are different strategies. So in which orinium-ion mechanism involves the generation of a cation, which is resonance stabilized, right? A similar slow rate first step, fast second. So rhenium-ion mechanism and SC1 both are stepwise mechanism, no doubt. One generates carbocation, the rhenium-ion. SE1 generates a carbene. This is the opposite. And then electrophile here reacts in second step. In rhenium-ion, it reacts in first step. So rhenium-ion mechanism have a second order kinetics, and so we can say SE1. We cannot say the other one SE2, substitution electrophilic bimolecular, right? So because both of them are not generating the same ion, they are generating different ions. So if they are generating same, then we could call the rhenium-ion mechanism as SE2 mechanism. But we doesn't call that SE2. So that's why this is SE1. The other one is rhenium-ion or Wheeland intermediate or sigma complex mechanism. So anyhow, these are the two mechanisms. Third mechanism, which is very rarely observed, is called simultaneous attack and departure mechanism. This is a aromatic electrophilic substitution reaction, but concerted. Single step. Previous two we have seen are uh, multiple steps, two steps containing. So they are stepwise, not concerted. But this simultaneous attack and departure mechanism is a concerted mechanism. I also exemplified this very little. Very few reactions are reported following simultaneous attack and departure mechanism. On the other hand, there are, let's say, 10-20% reactions which follows SE1 mechanism. Almost 90% reactions of substitution, aromatic substitution, electrophilic substitution reaction follows a rhenium-ion mechanism worldwide, right? Now you can see mostly it is rhenium-ion which operates, but to some extent SC1 also operates, and very rarely simultaneous attack and departure mechanism follows. So this is just a preview. You have come across to the aromatic electrophilic substitution reaction. Then we can convert the reactivity of our substrate in aromatic electrophilic substitution. Our aromatic system is electron rich. Now, let's say we can make its reactivity opposite. This can react with a nucleophile, but we have to make this substrate electron deficient. Now you see, we have made this electron deficient. So we have placed some electron withdrawing groups by resonance. So minus R groups we have placed. So now if we have a group which is X may be halogen, it may be phenyl sulfonyl or phenyl selenoxy groups, right? And similarly, it may be a sulfonyl groups as well, which are gold leaving groups, which leaves from here. So nucleophile shall approach the carbon which is electron deficient and kicks out this X from here. So this is a slow rate step. Second is fast because this negative charge is generated, not carbene is generated by the action of a nucleophile. Substrate is electron deficient. So due to minus R effect of these two nitro, I have presented the reason. This position, these two carbon, three carbons are electron deficient, too much. This carbon, which is remaining, is bonded with a nitro, which is also electron deficient. This carbon is also electron deficient, bonded with a nitrogen. Only this is a carbon which is not electron deficient to high extent. All right. So anyhow, this nucleophile approach, this carbon, which can leave a good leaving group. So which undergo the substitution of a group by a nucleophile. So this is a very simple reaction. You have seen the examples of these as well. Now, these are the two topics we have covered in this case. One, we have seen substitution, aromatic, electrophilic. Second category, we have covered substitution, aromatic, nucleophilic, right? So, but for this nucleophilic, we must have a aromatic substrate electron deficient. Then it can only undergo these reactions. So, some rules, some methodologies are associated with the substitution reaction collectively, electrophilic as well as nucleophilic. So I'm just going to present that as well. So in all these aromatic substitution, we have taken benzene ring system as a standard, but it doesn't mean benzene is the only aromatic system. There are so many other aromatic systems. We have just focused on carbocycle, aromatic but carbocycle, all carbon. Maybe a heterocyclic system is also there. So it also undergo aromatic substitution, electrophilic as well as nucleophilic. So just I'm extending this knowledge on some other substrates. Now look at, I'm extending this. You have seen aromatic substitution on phenyl ring. If it is phenyl ring, all carbon are same. They are identical. Any electrophile can approach any position, no doubt at all. But now let's see if the structure number one, this is commonly called naphthalene. The structure number one is commonly called naphthalene. Naphthalene, if you remember, just to add to your knowledge, this is used as a moth balls, commonly called moth balls. You have small insects, you are interested to prevent them. So this is used as an insecticidal property. If you remember, these are small balls, white color balls that we place inside the wardrobes or some places where we reserve the clothes so that some insects shouldn't get intact with these clothes. And those clothes which are being treated with mothballs, so they are not being affected by insects because the insects are being killed once they enter such chamber. So mothballs are basically naphthalenes. It doesn't have a high melting point. It has around 80, 90 melting point. So mothballs are normally used to kill the insects. So that's why insects doesn't affect the fabric materials. So this is the same naphthalene. So naphthalene, all carbons are not identical. Like comparing with the benzene ring system. Now look at here, this carbon, this carbon, and this carbon. These are the four carbon which are next to bridgehead. Look at here. This is a bridgehead carbon. This carbon is next to it. Similarly, this carbon and that carbon are next to that. So these four carbons are in same environment. Now look at here. This carbon, and these two carbons. They are in same environment. So in fact, there is no substitution possible at bridgehead carbon. These carbons are quaternary carbon, having no hydrogen which can be replaced. You see, this is bonded with two carbons here, one carbon this side, one carbon this side. So they are not participating in substitution. There are 8 centers here. 4 these are identical, and these two are 4 which are identical. So there are 2 substitutions possible. Substitution can take place at here or there. It may happen here or there. These two positions are same. These two positions are same. Very similar. This position and this position is very similar to this one. So we name these positions. This position which is next to bridgehead is called alpha. This is alpha position. And this position is called beta. This is also beta. This is alpha. Again, this is alpha. This is beta. This is beta. This is alpha. So there are 4 alpha positions. There are 4 beta positions. So electrophile can approach to any position. Electrophile can approach So this is arrow is presented. It doesn't mean this is participating in a reaction. This is showing the electrophile can be approached by these two positions. One is called alpha. This position is alpha. This position is beta. But it doesn't mean electrophile is donating electron. It can't donate because arrow we always present from electron rich to electron deficient. So if this is showing electrophile can approach this carbon, it can approach this carbon. These are the only two different carbons. In benzene ring system, all carbons are identical. But in naphthalene, all carbons are not identical in fact, right? So these are the two positions which are important. So any electrophile can approach here or any electrophile can approach this position. You shall see later why it prefers this position. It prefers this position. It doesn't prefer this one. Why? Because let's see if it adds to this. So hydrogen and electrophile shall make a bond. Positive charge shall be generated here. This positive charge shall be stabilized by this double bond, right? So this benzene ring doesn't involve here because if this benzene ring resonance energy intact, so this ring only stabilizes this positive charge, so it is shall be more stable. So under thermodynamic conditions, we get substitution here. You have seen already this. Under kinetically controlled conditions, substitution takes place here. Why? You have seen this before when it introduced thermodynamic and kinetically controlled condition. In thermodynamic, stability is important. So if this benzene ring system doesn't participate, if there is a positive charge, this double bond shall stabilize this. Now let's see if electrophile approach here, the positive charge shall be here. It cannot be stabilized by this point. Definitely this aromatic system should stabilize. So here stability of ion is not important, but steric factor is important. No doubt this carbon is sterically more crowded due to this, but here it is not crowded. So this is thermodynamic position. It is under thermodynamic condition, electrophile shall approach this one dominating. Under kinetic condition, electrophile shall approach this carbon, beta carbon. So this is a entirely different issue that you have already come across. Look at the structure number two. This is in fact a nucleus in which three phenyl rings are attached with each other. Very similar way. Now look at here, these two positions and these two positions are identical. These two positions and these two positions are also identical. So no doubt this is alpha, this is beta. This is alpha, this is beta, very similar here. But electrophile neither approach here, not approach there. It approach these two positions. This is in fact called carbon 1, 2, 3, 4, and this is 5, 6, 7, 8, 9, and 10. This is 9 and 10 position we call. Why we call them 9, 10 such positions? Because in this case, what happened is we are getting in fact, let's see, if I present this electrophile is approaching here, we shall get a positive charge there. What shall happen? This double bond shall donate this electron pair here. We shall get a double bond there and a positive charge here. This positive charge is here. You see one benzene ring, the other benzene ring, two benzene ring systems are having resonance energy, right? And this positive charge shall be stabilized by this ring as well as other ring. If it is adding here, so it shall be stabilized by this ring only, right? If it is approaching here, so we shall get a positive charge there, right? So resonance energy shall be disturbed. So under thermodynamic conditions, it shall not prefer here, but under kinetic condition, it shall prefer these positions. So this is for this nucleus number 2. This is commonly called anthracene. Now look at another one. Here three phenyl rings are also attached, but differently. You see here this ring is not attached here. This is attached to this position. So these are the three rings as well, but in different way. This is called phenanthrene. This is anthracene and this is phenanthrene. Now see, there are isomers of each. In this case, numbering starts from this carbon, oops, this carbon and that carbon, right? Similarly, this carbon and that carbon, they are identical in fact. Four position identical. So these two positions and these two positions are also identical, and these two positions are different. This is very similar to this. These four positions are same here. These four positions are same. These two positions and these two four positions are same. Here very similar to them. Four positions are same. Here these two are different. Here these two are different. Now electrophile here again shall approach this position or that position, right? Why? If it approach here, positive charge shall be generated here. Two benzene ring system resonance energy shall be intact. If it approach here, then the resonance energy shall be decreased. So this is how I that we shall have instability. So under thermodynamic condition, the electrophile shall prefer these two positions. So this is carbo cycles I have just exemplified other than benzene ring system, and keeping in mind benzene is not an IUPAC name. So what is the IUPAC name for benzene? It is called phene, Phene, phene. Like we'll call this naphthalene, anthracene, phenanthrene. So phene is the IUPAC name for benzene. Very little people, very less number of people know these things. It is phene. That's why we call it phenyl group. We doesn't call benzyl group. Why? Because benzyl is something different. Benzene ring attached to a CH2 is called benzyl. Benzene is not IUPAC name. Phene is the IUPAC name for that. I hope you should already know. PHENE. You see all of these, naphthalene, anthracene, phenanthrene, all of them are ending with ENE. So benzene is also ending with it, but it is not IUPAC name. Phene is the IUPAC name for benzene. So this is the aromatic substrate, which are carbo cycles I have highlighted. But now let's say if we have a tetracyclic system, very simple benzene ring system having a nitrogen. This is a commonly called pyridine. Pyridine is a common name, but its IUPAC name is azine, if you remember. And structure number 5, you see the same nucleus is fused with a benzene ring system. We have fused that. This is called quinoline, commonly called quinoline, but its actual name is benzo-1-azine. One position, 2, 3, 4. This is 5, 6, 7, 8. So this is called quinoline. This is the common name, but actual name is benzo-1-azine. And next one, here a 5-membered ring is fused with a benzene ring system. If there is no benzene ring system, this is commonly called pyrrole. Pyrrole is the common name. Actual name, IUPAC name is azole, right? So this azole is fused with benzene ring system. This is commonly called indole. Indole is a common name, but benzo-1-azole is the actual. Now, if we are using this, where shall be the electrophile approach? In this case, keeping in mind the effect of this nitrogen, it has a non-bonding electron pair, but keeping in mind this nitrogen is sp hybridized. Its lone pair is parallel to the plane of this. The pi orbital here and here is perpendicular to this plane. And this lone pair on nitrogen is not perpendicular, it is along the plane of this paper, right? So there is a 90-degree angle between these two orbitals and this non-bonding electron pair present on nitrogen. It cannot donate this. Only resonance is possible if two orbitals are overlapping parallelly. These two are not parallel. They are perpendicular to each, 90 degree. So they cannot overlap. That's why this nitrogen is not contributing electron pair. Just like here in pyrrole, this nitrogen have a non-bonding electron pair, so which is along the plane of this pi orbitals. So it can transfer electronic density, so it shall contribute. But in this case, pyridine, it is not contributing. So what shall be the resonance form? It shall take this electron pair off. So we shall get a positive charge here. It shall be stabilized by this, making a positive charge here, positive charge here. So ortho and para, it shall generate electron deficiency. It means there are less electrons present here. So where electronic density is available, it is available at these two positions. Both of these two positions are symmetrical. These two positions are symmetrical. So what shall happen? The electrophile shall approach meta position to nitrogen. Meta. This is ortho, this is meta, and this is para position. So electrophile shall approach these two positions which are identical. Now let's see what happens here. Very similar. Here this carbon which is meta. So this is been substituted with a bridgehead carbon. So it cannot take place. Only one position is possible, which is this one. Any electrophile, whenever we shall react with quinoline, it shall approach this position. In pyridine, it shall approach either this or that, which are identical in fact. They cannot approach this position, they cannot approach that position in fact. Now proceed further towards endole. Here this behavior is totally different. What happens in this case? Let's see, if I present this lone pair, it donates electron density, and this electron density transfer here generating a negative charge at this position. So electron density is much rich at this carbon rather this one, because this is bonded with nitrogen, slightly electron deficient. Here inductive effect is poor, but due to resonance effect, it has a negative charge. So substitution shall take place at this position, electrophilic substitution. So why it is not taking place in the aromatic? Because there are other resonance forms in which you shall get a negative charge here, negative charge there. Why it is not taking place? If this negative charge or positive charge is remaining within this heterocyclic ring, doesn't enter the benzene ring. So this benzene ring shall be more stable, having more high energy. Let's say if it is involved in this, then resonance energy shall be decreased. If resonance energy is decreased, stability shall be decreased. So that's why mostly when we are doing electrophilic substitution, we have high temperature normally. So why? To make the stability factor in count. So thermodynamically controlled reaction normally we perform. So in this case, substitution C taking place in this heterocycling, not affecting the benzene ring. Again, here it is happening here, not other positions as well. Because if it is happening here, then it can happen here, then it can happen here as well. So, but it is not happening there, it is happening as this ring to under thermodynamic condition. But if it is kinetically controlled condition, then it can be a mixture here, here, and there. So I think this should be much clear. If we have other aromatic systems, so then we can predict their reactivity as well. Proceeding further. No, just look at here. This is the orientation of an electrophile. So first, I have presented phenyl ring, and you have seen some other rings present. But what I'm giving you a concept is the orientation. In previous class, you have a little knowledge of this again. So I'm just going to repeat this with different aspects. In previous semester, you have come across about the uh, rules of resonance, right? And you have come across, you have studied them, stability of the factor, more resonance form, more contribution. So if any molecule have more resonance form, mean canonical forms, it shall have more resonance energy. More resonance energy mean more stability. More stability mean less reactivity. You have seen in the beginning of this course, reactivity and stability are totally opposite to each. If one thing increases, the other decreases. If stability increases, then the reactivity decreases. If the reactivity increases, then the stability decreases. So both cannot go side by side. They are totally opposite to it. Stability and reactivity are totally opposite. Benzene ring system is called more stable system. It means that's why it is less reactive. We need to heat this just to provide energy for reactivity. This is the reason. So theoretically, there are different aspects. If already, let's see, we are not having simple benzene. We have a substituent X present already on benzene. If we carry out electrophilic substitution reaction, so this electrophile, if it is X is hydrogen, then all such positions are different. This electrophile can approach any carbon, which shall be identical. But let's see, if already a group is present there, X group is present, now either this electrophile shall approach this position and that are same, this position and that position are same, and this position is only one. This position you are familiar to next to a substituent which is commonly called ortho position. These two positions are called meta positions. This position is commonly called para position. So this electrophile have an opportunity. It can approach this carbon, it can approach this carbon, it can approach this carbon. So three different carbon positions are possible for this electrophile to approach. Where it approach, I have highlighted that it can approach rhenium ion mechanism shall generate a positive charge, then it shall undergo loss of H positive ion to generate this entity. So I'm not showing the mechanism here, just the products. So this electrophile theoretically can approach here, it can approach this position, and it can approach. So product number 2, 3, and 4 all are possible. Now, it depends upon the nature of this electrophile. It shall approach this or that, or it depends upon the nature of this group already present on this aromatic system. Experiments has been done, and this has been coming to us that if it is not dependent upon the nature of electrophile, if it is nitronium ion, it shall follow this one, and the other one follow this one. The third kind of electrophile follows this. No, not at all. It is not the electrophile which makes a difference. It is this substituent X which makes a big difference towards reactivity. This is we call orientation, where it is directing this electrophile to approach either to ortho, meta, or para. So this is done, this is controlled by this group present on this aromatic system, not only on benzene, in any aromatic system. This is the group which controls this. Now with respect to this, I can divide this into two categories. This X may be a group which contain a non-bonding electron pair present on it, just like I have presented here. So if it has non-bonding electron pair, it may be halogen, chlorine, bromine, iodine. It may be oxygen family, oxygen, sulfur, etc. It may be nitrogen family like nitrogen, phosphorus. Nitrogen have and phosphorus have only one non-bonding electron pair. Oxygen and sulfur have two non-bonding electron pair. Halogens have three non-bonding electron pair on them. So these are the only 8 elements. If any of them is bonded directly here, so it shall follow this mechanism. This lone pair shall be delocalized, generating a negative charge here. So we better log in again because